We're going to have a little light relief from the Brexit debate this week by taking a look at the Monty Hall Problem. It's based on a game show that was hosted by a chap called Monty Hall. So let's set the scene first. A game show host offers you 3 doors. Behind one door is a car and behind the other 2 is a goat. To win the car, you just need to choose the door that conceals the car. The location of the car is random, so each door has a 1/3 chance. Now let's suppose you choose this door. Now the host opens this door and reveals a goat, and then asks if you want to switch to the remaining door. So the question is, should you switch? Now if you do switch, your chances of winning the car are doubled from 1/3 to 2/3. So first of all, you chose this door with a 1/3 chance of winning. So the chance of the car being behind one of these 2 doors is 2/3. Then the host opened the left-hand door, so the chance of the car being behind that door we now know to be 0. But the chance of the car being behind one of these 2 doors is still 2/3. So the chance of the car being behind the middle door must now be 2/3. But don't forget, this is only a chance. We're talking about probability. There is still a 1/3 chance that the car is behind the right hand door. Now we built a spreadsheet to simulate this, and here it is. First of all, I'll zoom out so you can see the whole thing. There are just a few columns of calculations which run to 1,000 rows deep. To start with, we have 2 random number columns to decide which door hides the car and which door we guess. The next block contains a flag showing which door we actually chose, and once we have that, then we have the information Monty needs to choose one of the other 2 doors. If we chose a door with a car, he has 2 choices, but if we picked a door with a goat, he only has 1 choice. So some of these rows have 1 flag and some have 2. Next we have 2 helper columns. The first one shows how many choices Monty has, and the second one always generates a random number of either 1 or 2. This random number is only used if we pick the car door with our initial choice and Monty has to choose one of the other 2 goat doors. Now we have enough information for Monty to open a door, and the next 3 columns work out which one he should open to always show a goat. Once he's opened one of the doors, we have 1 choice to switch to, which is the next block of 3 columns. And let's scroll right a bit to see the other columns. Now these 2 columns summarize the earlier calculations showing what we originally chose and which door we had the option to switch to. And the win columns show whether we would win if we stuck with our original choice and whether we would win by switching. Now the table at the top counts the number of wins for each strategy of our 1,000 tries, each row representing one of our tries. And that gives us close to 1/3 and 2/3, but this isn't stable based on only 1,000 rows. So next we built a data table, and that's going to effectively run our 1,000 rows an extra 100 times. So if you're not familiar with a data table, it takes a table of input values and passes them through the model one after the other. Here all we want to do is to recalculate the model 100 times to give us new random numbers. So we're cheating a little by just referring to cell A1 in the data table, and then we record the probability each time. So actually the data table just references A1, there's no formula there, it's just to force a recalculation. The data table has 100 rows, so we have a total of 100,000 samples. Now these are summarized here at the far right of the worksheet, where we can see the probability resolving to 1/3 for sticking with our original choice and for 2/3 if we switch. If you'd like to download the spreadsheet and look at it in detail, then click the link at the top of the YouTube video and you can go to our website and download this file. I hope you enjoy grappling with the problem and that this has helped make some sense of it. Thanks for listening.